All right, gang, let's take a deep breath and think about what we accomplished in the previous video, making a transition into fitting our first mixed model. Um, all right. First thing, we have determined that a mixed model is a good choice here. Why? First of all, it allows us to use all the data, resulting in a higher sample size. But most importantly, it allows us to account for the correlations between the data coming from different districts, because in the previous video, we showed that was problematic. Uh, More importantly, or equally importantly, we will have fewer parameters. Remember, we had an insane, 48 parameters if we looked at 8 districts and 3 instructional techniques and 2 predicted or 2 estimated coefficients within each. And we can avoid the problems with multiple comparisons that we're sitting here staring at under coefficients. So guys, what we need to do, first of all, it's going to be kind of cool. We need to install the package LME4. So install it, or I have already, because I've toyed around with these models quite a bit in the past, I'm just going to access the library. Now, let's review some stuff again from the first video. First of all, let's talk about fixed and random effects. Fixed effects we can think of as being variables that are expected to impact the dependent variable. Back to simple linear regression, same kind of terminology. In our situation here, in our example, pretest is our fixed effects, and post-test is clearly our dependent variable. Random, now in a random effects are usually grouping factors. And in fact, with R, they have to be categorical because R won't allow you to force or treat a continuous variable as a random effect. But guys, we typically aren't interested in the impact of the random variable on the dependent variable. We just want to know if it might, if it, the random factor, the random effect, might be influencing the patterns that we see. Now, specific to our example, district could be a fixed or a random effect. It would be a random effect if it's a random sample of all districts. It could be a fixed effect if these were the only 8 districts in which a student may be enrolled in the 3 tracks. Guys, we don't care about comparing performance in school districts. If we did, we could use an ANOVA. We're looking again, and I hate to be so redundant, but it's just extremely important that we keep our eye on the prize here. We are interested in, we want to know how much variation is attributed to district association when we're trying to predict post-test scores. So guys, in our case, we're looking to control for the effect of district. We can assume that we haven't sampled all districts in the world. Moreover, we hope that our results are generalizable to students from other districts. What I'm trying to say here is district needs to be a random effect. We also know that the test scores within each district are highly correlated. We saw that from our box plots, right? So we want to address that. So guys, for what it's worth, if we specifically chose 8 particular districts and we were interested only in those 8 districts and wanted to make predictions only about those 8 districts, then the district would be a fixed effect. But guys, we want to make a larger statement, a more broad, more generalizable statement about the impact of pretest on post-test scores, just controlling for the variation within the districts. All right. I think I've beat a dead horse there, but again, it's just important that we keep our eye on the prize here. So let's fit our first model. Okay. So again, we have a response variable post-test. we want to explain the part of the variation in post-test through fitting the pre-test score as a fixed effect. But the post-test score has some of this this unexplained variation that is associated within the districts. So by making it a random effect, we are modeling the unexplained variation through its variance. All right, so guys, variation, just a generic word for how much something spreads, variability. Variance is a particular statistical term, at least in my opinion. So our question changes slightly. We still want to know if there's an association between pre-test and post-test, but we want to know if that association exists after controlling for the variation that we observed in the districts. So I'm going to call this a mixed model. Drum roll, please. LMER. So I want to model predict post-test from pre-scaled. And I want to find my vertical line. Always afraid I'm going to make a typo there. All right. Now, wow. Okay. Interesting. What we see is, well, the very first thing I look at is still. I mean, it's hard to teach an old dog new tricks. First thing I look at is the effect of the fixed effect, and again, that's the pre-test score. And we can see that the t-value is small. You can get that just from these two values. You see that the estimate is much larger than the standard error, meaning that we can't distinguish that beta coefficient different from 0. So next thing I'd want to look at is I'd want to come up and examine the random effect. And we can see the district, that the variance associated for district is 340.9. The unexplained variance is 223.5. So guess what I can do is I can take 340.9 divided by 340.9 plus the residual variance, 223.5. And I get 60.4%. So what I can say is that about 60.4, well, about 3/5 of the variance, well, no, let me back up. Guys, that's a lot of variation, isn't it? So again, as we expected, there's something going on within district. There's more going on within district than there is just the relationship between pre-test and post-test when we control for the random effect. So ultimately, we can say that the differences between districts explain 60.4% of the variance that's left over after the variance in post-test is explained by pre-test. I'll tell you what, let me write that out if I can possibly repeat that. The difference between districts explains approximately 60% of the variance that remains after the variance in pretest is explained. It's not right. Is explained by pretest, pre-scaled. All right, interesting. Well, we run a model, so we should take a look at the assumptions again. So let's look at plot MM. And looks pretty good to me. No